Cool. All right. We'd like to welcome up next Dr. Hudson Smith, Assistant Research Professor of Electrical and Computer Engineering at the Watt Family Innovation Center of Clemson University. His research focuses on utilizing natural language processing techniques in the social sciences. Take it away, Hudson.
Hudson, you're muted.
Can you hear me now?
Yeah.
Yep.
Okay, but I can't hear you for some reason. I'm sorry. I was hearing you fine until the. Let's try again.
Can you hear us now?
Okay, I can hear you now.
Good.
Okay, sorry about that, everybody. Let me just share my screen here. So I actually don't know what introduction Naomi gave me, because that's about when my audio cut out, but I'm sure it was very nice. Thank you for inviting me to share here today. Just a little bit about myself. My name's Hudson Smith. I'm a research faculty at Clemson University, jointly between Clemson's Watt Family Innovation Center and Department of Electrical and Computer Engineering. My position is a little bit unique in that my primary role is leading this program, which we call the Watt AI program, which I'll tell you a little bit more about. And our whole mission is facilitating applications of machine learning and artificial intelligence here at Clemson. So it's not purely a infrastructure technology support role. It combines infrastructure technology support and consulting on how you apply machine learning techniques to lots of different research domains. First, I'd just like to acknowledge some folks, IBM, for generously giving us access to their cloud platform to conduct the research that I'll present to you today. Also, Clemson's Creative Inquiry Program, which is a large undergraduate research program here at Clemson that facilitates activities such as the activity that I'll describe to you today, and just the many amazing students and faculty that have participated with me on this research. The talk today will be something of a zooming in from a very large context into a very specific one. I'll just tell you a little bit to start out with about the Watt AI program, which I referenced earlier, and what our goals are and the unique problems that we face in the program, because I think these set the stage for understanding our specific cloud needs and some of the approaches that we take. And then I'll zoom in further to talk about a subcategory of the types of projects that we work on focused on social media research. And then we'll talk about a specific case study. And throughout, I'll kind of make references to the role that cloud computing has played and will probably play in the future in this work. So first, just a bit about the Watt AI program at Clemson. This is a picture of, I'm over there on the right, and the gentleman standing next to me, Carl Ehret. He and I co-lead this program, and in a given semester, we have about 30 students. So this is a few semesters old, but with those 30 students, we work on lots of different projects here at Clemson, as I'll discuss in a little bit. At the highest level, the purpose of the Watt AI program is to support AI education and research at Clemson University. So more specifically, we came to this program trying to answer a few specific challenges. One was, how do you leverage ML and AI techniques beyond the traditional computing disciplines? So what we observed is that in computer science and in electrical computer engineering, the groups that needed these techniques were able to incorporate them into their research workflows. And it was by bringing on graduate students who had an interest in machine learning and AI, they were able to sort of pull in machine learning and AI into their research agendas and then benefit from that new capability. But outside of the traditional computing disciplines, there was not that ease of pulling in these new techniques. So how can we overcome that obstacle? Our goal structured around that obstacle is to kind of to fill the gap, so to speak, to consult with folks, sit down with folks, talk to them about their research, try to really understand what their needs are, and then try to help them formulate a plan, a research plan that incorporates, if appropriate, machine learning techniques. And if not appropriate, then go our separate ways. So just providing that expert consultation so that they can even know what's possible or what's not possible, and then executing on that plan, putting together teams of students and faculty and grad students, postdocs, to execute the research plan as possible. Connected to this, we wanted to also equip students from many different disciplines. In keeping with the idea that disciplines outside of the traditional computing disciplines are having trouble integrating machine learning and AI into their work, it's also the case that the students in those disciplines are just not really being trained to have the competence they need to succeed in applying machine learning and AI to their work. And so what we've done to try to address this is we've designed a course that accepts students from any major, and we have a very broad scoped curriculum that we put students through when they join this course to try to equip them to become effective thinkers and doers within their domain, but at least competent in thinking about what's possible with AI and what's harder. And then if they're technically inclined, actually giving them the skills they need to do the work that they're interested in doing. And in keeping with both of those goals, we also want to make this self-sustainable. So we partner with faculty from all different disciplines and support them as they're trying to develop grant proposal activity around concepts that they have related to machine learning and AI for their research. So this is the slide where I brag about our many accomplishments. The program started in 2018, and since then it's grown from, we had 6 students our first semester, and now we have about 30 each semester, and about 12 active projects each semester that we work on, including over the summer. Through all this activity, we've helped support 26 different proposal submissions, a mixture of internal grants and external. And we've had 12 awarded submissions, more than a dozen conference presentations, and 6 peer-reviewed publications with many in the pipe. And it is truly interdisciplinary. We've touched 6 of Clemson's 7 colleges. The only college we haven't is actually science, which might surprise you. And 30 different faculty from 22 different departments have worked with us so far, and many more to come, I hope. I would be remiss if I didn't also talk about sort of the diversity of students that we've recruited. So far, I think it's 82 students have been through our program, and we have another batch starting just in a few weeks here in the fall term. About half of our students are from computer science and computer engineering. We make a very intentional effort to recruit broadly, but the subject matter is such that we get most hits from those areas in our recruiting attempts. And then we have a long tail of students from all different departments with a lean towards more technical fields, with a few exceptions. This is a look at the variety of projects, both in terms of subject matter and in terms of the type of data that we're working with on the various projects in the Watt AI program. So you'll notice that a lot of these are not in the hard sciences. A lot of these are in social science, the social science domain, healthcare, education, politics. And then we have kind of a grab bag of other projects. And we have projects involving text data, imagery, and lots of other stuff. I think because of our attempting to fill the niche of people who are outside of traditional computing disciplines, many of our projects have turned out to involve analysis of social media data, as highlighted in green here. This project, facilitating qualitative analysis, we're working with some faculty in the College of Education who do this process that some of you may have heard of called emergent coding. And in emergent coding, you look at a corpus of text. It could be hundreds of thousands of open-ended survey responses, and you try to come up with a set of codes or labels for that data that you think is representative of the data and tells you something interesting about the data for your research objective. And then you analyze the data through that frame, the frame set by the codes that you arrive at. And this is a very human process of introspecting the data and thinking about it and discussing with your colleagues what makes the most sense and consolidating labels together. We're trying to develop some techniques to aid in this process. So can we look at the whole data set, these hundreds of thousands of survey responses, and incorporate the expertise, the knowledge of the researchers to somehow get a better set of emergent codes out at the end. Disinformation campaigns, this is a hot topic right now. We're working with some faculty in the Department of Economics here at Clemson and also the Department of Communication who study foreign actors with non-genuine activity on social media platforms and trying to understand those behaviors, try to categorize the different sets of activity to understand what are the strategy and tactics and the influences of those behaviors. Yeah, and then more. I won't talk about them all. The one we're going to focus on today in the case study is actually this congressional tweets one. And in this case, we're studying all the social media, specifically Twitter messages from the US House of Representatives members and their staffers, and trying to understand their behaviors and the influence of those behaviors on social media platforms. Now I'll just say a few words specifically about the role of machine learning in analyzing social media data. So machine learning is not the only tool you might bring to bear when studying social media data, but I'll talk about how we're using machine learning and what we hope to get out of it and what we've gotten out of it so far. I'll also say a bit about the role of cloud computing in all this. So machine learning, well, most of you are probably familiar with the idea of machine learning, and probably your intuitive notions about what machine learning is and can do map pretty well to how we're using it for these projects. There are many ways you might use machine learning, and I'll just really talk about the workflow that we have come across most frequently. One way to think about machine learning, if you look at the diagram on the right, the process of training a machine learning model is a process that takes as inputs data and labels, usually generated by humans, but sometimes not, for that data. And this process occurs, and the output is an algorithm, the machine learning model, it's commonly referred to as. And this could be a deep neural network, it could be a random forest model, or any result of any machine learning model. And then that's not the end of the story, though. We don't care about the model for its own sake, usually in machine learning, though there are exceptions to that. But we want to take the model and we want to do stuff with it. And what do we want to do? We want to generate predictions on more data. So we take more data and we generate predicted labels for that data. And these labels should be good facsimiles of what we would have gotten if we had spent the human effort or other means to generate the true labels. And how do we use this for social media research? Well, the basic idea is these labels, this data and these labels, it's easy to generate lots of data via social media platforms. You can just scrape social media platforms for millions of messages. What's hard are getting these labels. This represents the expertise of humans. This is man hours woman hours, and very, very difficult to, maybe you can get thousands, or if you're working very hard, maybe you can get tens of thousands. But getting hundreds of thousands of labels is out of the question for most research groups. But we want to be able to do analyses of hundreds of thousands or millions of messages. So how can we capture the expertise of human researchers on a small set of labeled samples and then apply that expertise to a large set so that we can then analyze that large set to understand the social phenomena that we're interested in from the research point of view. So the purpose of machine learning here is really to bootstrap the researcher's expertise from a small set to a large set so that we can then study that large set. So the story is not over at the end of the machine learning model. The story then kind of begins for the researcher. Some examples of this in our projects, we classify these political tweets according to their topic, and this is a supervised topic, so one of 30 common categories of political messages that you might be interested in studying. I mentioned the qualitative analysis project where we're doing emergent coding and sentiment analysis types of things and the dynamics of sentiment through time. We've looked at those as well, and I'll show you some more specific examples later. Okay, so quickly, let's just break this down into a few discrete steps that you'll go through when you're executing a machine learning project involving social media data. There's a collecting data phase, and traditionally what we've done and how we started out, or I call it our default approach, has been to write and run the code locally. The challenges with this is I write some Python code that I understand. The researchers that we interact with often are not prepared to take that and then use it in all the different diverse ways they want to use it. So that's a challenge. It's also slow to adapt to new problems because it's not, because the software is not, it's kind of an ad hoc or bespoke solution. It's not really designed to transfer to a new situation very well. And probably the most fundamental problem is our data, it's just hard to keep the data up to date. So for many of these projects that we're working on, the researchers always want, oh, there was this new political event and I want to see how the data moved in response to it. That involves, running the data locally again. And we would like to be able to we'd like the data to just be up to date for us. So some of the solutions to these challenges, the first set of challenges is just, better software design, turning some of these bespoke solutions into tools that are more repeatable, easier to hand to the researcher, or just easier for us to run ourselves. And then for the always out of date problem, running these things in the cloud has been a big help for us. We can run cron jobs on our own machines, but then you have to keep your machine running all the time, and it's just a pain to keep track of that. So just having the convenience of running some things in the cloud has been a great help to us, even though it's not fancy. It's just running simple code. It's not there's not a lot of intensive computing or anything. It's just really for convenience. Labeling the data. So this is a big part. This is a huge. It's easy to just gloss over labeling the data, but it's a huge component of what we spend our time on. The default approach has been, annotate the different labelers, annotate local copies, and then we collate them together. And this just is a nightmare. File versions, redundant files, and trying to figure out, oh, which data set were you looking at? Oh, we're actually using the next one now. And then things like setting up intercoder reliability tests where you have multiple reviewers label the same set of data and then compare, having to do all of that by hand. So basically the solution that we're using here is shifting our data labeling to some cloud hosted labeling tools. And to reduce the burden, actually, the number of labels required, we are pursuing an active learning workflow where the modeling process and the labeling process are wrapped together. And in order to do that, you kind of need your model training to happen in the cloud so that the so that the loop can be closed automatically in an automated fashion. If you're just training your model in a Jupyter notebook, and it's hard to do active learning. And I'll say a little bit more about active learning later. And just to speed along, cleaning the data is another big step, and actually training the model as well. And I alluded to that a little bit with the active learning thing. Okay, so just to summarize the places that cloud computing can help us: automation, so just regular data collection. The cloud helps us do that in an automated fashion. Storage, we were talking about storage in the previous talk. Here, the issue is not so much scale. We have lots of little projects. We don't have the volume of data discussed in the previous talk. So it's more a matter of convenience and standardization. The cloud gives us a way to standardize the storage and access of data. And then data labeling, I mentioned in the previous slide. And active learning. So if we want a project that involves human-machine interaction in an automated way, we really need something like the cloud to facilitate that. Especially when you consider that many of our reviewers are scattered across the world. And so we can't have them come sit in front of a local machine. We could perhaps host something and have them interact with that, but might as well put it in the cloud at that point. Okay, and this is just a diagram showing how active learning works for those of you who might not be familiar. Active learning involves fitting the data incrementally to incremental chunks of labeled data. So you'll start with a little bit of labeled data, and then you'll ask your model, you'll train your model on that little bit of labeled data, and then you'll ask your model, okay, go get me some samples to label that are going to be useful to you to improve your model, to improve the model. And it will give those samples, and then you label those, and you wash, rinse, repeat. You keep sampling the data to label, which the model estimates will be most effective at improving the model. And this can really bring down the number of samples that you need to label to get the same level of performance. And that's a big issue for us, because we're the doctors and researchers that we're working with, it's really hard to get their labeling time, and this can help us bring that down. Okay, so here are some example cloud architectures. I'll just start by saying I am not a cloud guru. I'm a data scientist, and as I approach cloud technologies, my #1 priority is like, what's the most convenient way I can get this done? And that would be different if I were dealing with huge scale problems with lots of users, as in some of the other talks. So I'll just talk about two: data collection and storage. This is the automation task that I mentioned to you earlier. We have a application running on IBM Cloud Code Engine, which is a serverless service on IBM Cloud. And its job is to every now and then go and get the new messages off of Twitter and pre-process those in the way that we need them pre-processed, and then put them in our relational database so that the researcher can access them from SQL or some dashboards we've set up, or possibly through integration with other apps down the road. A few things about this, often when you're talking about serverless and auto scaling and all that, the idea is, oh, it auto scales up when you need it to. I mean, for us, we're very cost sensitive on many of these projects. And so actually the ability to scale to 0 is really the most important thing for us, because the jobs that we run every 15 minutes only take about a minute to complete. And this allows us to not pay for any compute for those other 14 minutes. So it just saves us money. So that's one real benefit to this serverless approach for us. And this is just a rundown of one of the projects that we're working on, the data that we've collected so far over about 3 months running this data collection platform. Some of the challenges compared to running things locally: developing for cloud is less intuitive for a lot of researchers. So for myself even, and for members of my team, you can kind of be sloppy when you're doing things locally. You're looking at standard out on your machine and you can say, oh, I see, I need to rerun this part. But when you're running it on the cloud, on some serverless platform, you have to be a lot more careful about exception handling and logging and all of that stuff. So that's a good thing and a bad thing. It helps you develop better practices, but it does slow down the initial development. It introduces a cost that you need to take into account if you're thinking about switching. Also, though SQL has many conveniences, many of our research faculty partners are not comfortable with it. So we have to develop ways to give them access to it, or just be content with being the interface ourselves. When they say they want the newest data pull, we go get it. So, okay, this is the active learning workflow that we've developed. Here, this is a little bit more complicated. We have a code engine-based application here. Now it's a code engine app, so it's serving HTTP requests, namely to get new labels as they come in through this service called LabelBox that we're using. And when some new model retraining criteria is met, triggering off the retraining job. And then when that is completed, triggering off a job to sample the new data for labeling. Some challenges that we're facing here. So serverless requires stateless app development, as you probably know, because these servers, the code engine jobs are ephemeral. They go away when the job completes, and that just can be a little bit of a pain in the neck if you're coming from a traditional local development background. So we use Redis as a key value store to capture any state that we need. Also, training machine learning models in the cloud is no joke. Via API calls, it just introduces a lot of complexity. You have to script everything very carefully so that all the cogs fit together very well, and you're not there to guide things as if things go wrong. So that just introduces a good bit of overhead that's probably not justified in lots of one-off cases. So if you're just training a one-off model for a specific use case, it's really probably not worth it. But in this active learning case, we need to train the model many times over the course of weeks as the data is being labeled, and we can't be going to the Jupyter notebook every day and then uploading the model manually, et cetera, to support that active learning process. Okay, so moving along. This is an example of the labeling interface that we're serving from our code engine application. You can see the different options. So the researcher would read this tweet and check any boxes that they thought were appropriate. And then once that was checked, a webhook into our application would be triggered, and we would capture the label data and do stuff with it. Okay, so here is a specific project that I'm going to dive into this specific project that I've kind of been alluding to all along. This is working with Dr. Jeffrey Fine in the Department of Political Science here at Clemson University. His focus is on election politics with an emphasis on the US Senate. And we've been working together for a number of years now. It's just been a real joy to work with him, and we've done a lot of interesting things together. So that's kind of why I chose this particular project as a case study. This team we've had some amazing undergraduate students as well. Here's a team from a few years ago who presented and got best paper at one of the premier political science conferences in the country in 2019, best undergraduate paper. And this is Jeff. So here's just a very specific workflow for one of our sub projects on this project. I'll draw your attention to the diagram at the bottom. The machine learning model, this is kind of the steps that we go through with the machine learning model. We take our tweet text that's just made up text here, and we have to pre-process it somehow. And then we run it through the model and predict something from it. In this case, I'm showing attack confidence, which is one of the factors that we studied. So we're training these models. We're collecting this data for various tasks like this. and training models for several different definitions of, what is our target data, what messages are we looking at, and what kinds of things do we want to get out of those messages. Here are a few examples of that specifically. So this actually is built on attack confidence that I just showed you. This is showing the percentage of messages that contain political attacks as a function of time, split out by party. And I'll let you speculate as to the source of the dynamics that are on display here. But these are the kinds of things that we can start to study, and we can start to connect these dynamics to the substantive political science questions that are interesting to this faculty. For instance, learning from negativity. So there's the theories about how does one's use of negativity influence others. We were able to show that you learn differently from different groups, and you're more likely to resort to attack messages from groups that you sort of are more in with than groups that you are not in with. We also looked at how the issue content of the messages affects the spread of those messages. So this is just to give you a flavor for some of the questions that we're addressing with this project. And some of the pain points I've already mentioned. Each time we have a new task we want to solve, there's a lot of manual effort in pulling the right data, and or updating the data to the most current state in time, or transitioning to entirely new projects is very costly as well. So the keeping data up to date is almost completely remedied by cloud deployment. Oops. So we're able, I mentioned this this cloud architecture where we automate the data collection process, that has solved this keeping data up to date problem for us. And then on the agency, so this has been another big problem. The researchers not having access, not having the ability to pull data themselves or ask questions about the data themselves, and kind of being reliant on us. So by converting some of the bespoke solutions to tooling, we've been able to put more agency into the hands of our research partners, so they can run their own ad hoc data collections. They can interact with the data through SQL clients and dashboards, though this is actually kind of challenging, and it's still a problem we're working on. Data cleanliness. So running the data cleaning processes in a standardized pipeline in the cloud has sort of removed a lot of the problems that we had when as we were getting new data, pulling them into a notebook or Python script and running our pre-processing and saying, oh, we'd like to make this tweak. And so we'd have different versions of our pre-processing code in different notebooks for different tasks, and it just became a nightmare. So we've been able to clean all that up. And then the timeliness aspect, this is the most important one. We've been able to keep our data real time and answer new questions as a result. And this is just an example, and this is, I'm nearing the end here. This is an example of the sorts of things we can start to dive into now that we have data every 15 minutes. We have the state of the data. This is showing the reaction counts to 6 odd Twitter messages as a function of time. This is an easier way to look at the data. This is the total counts as a function of time. You can see when the message landed on Twitter, the reaction counts quickly go up, and then they slowly, they plateau. And so we can start to we can start to look at these dynamics and understand this. And this requires you to poll Twitter every 15 minutes to get the state of those reaction counts. And now we can do that. These are just a few of the open source projects that we've developed to support this. I won't go into these. If you're interested in these specifically, reach out to me and I can share them with you. They are definitely works in progress. So to conclude, migration to the cloud comes at the cost of greater complexity. At least that's been our experience. And so you have to be thoughtful about which parts of your work make sense? Where does the cost benefit analysis prove out? For us, it's helping with streamlining many of the tasks that are repeated across multiple projects, and then the real-time component that I mentioned, and any systems that involve this human-computer interaction where you need some computing to facilitate that interaction. The cloud is kind of a natural place to house that computing. All right, I think that's it. So if there are any questions, and if I've left any time, I'm happy to answer any questions.
Thank you, Hudson. And thank you for telling us about the Watt Center. It sounds like a really, really cool interdisciplinary space for applying some of these technologies. It's always heartening to me as a data scientist to hear about places like that. So we have a few questions that we've collected, and also just a reminder, if you have any questions, then drop them in the chat. I think there was some really great foundational information about a whole lot of topics in this talk. We have one question. You have a lot of cool information here about the role of the cloud in the projects that you've built, but this question asker was interested in what made you decide to pursue a cloud approach from the beginning versus a local approach using only computers that you have physically.
Yeah, mainly the pain points that I discussed. We didn't pursue the cloud from the beginning, actually. So all of the pain points that I mentioned were not hypothetical. They were real pain points that we got ourselves into. And so the pursuit of using the cloud was to try to alleviate that. I mean, the real kicker for me was this real-time application. The researcher was really interested in understanding dynamics through time. And for that, I needed to be able to see the data through time. And we just weren't able to do that before. So, and then that was kind of a foot in the door. And so there's been a number of other smaller things that I have moved to the cloud out of convenience. We're still very much, we have a lot of things going on locally. I mean, in data science, you have all these ad hoc one-offs that you try out, and there's no sense in moving those to the cloud because it's not a repeated workflow. It doesn't need to be reliable, robust. You're just testing things, and of course, we still do all of that locally.
Cool. I love how that highlights this aspect of the cloud that I think is really powerful, which is how it can be so dynamic. Like when you hit a stumbling block, you can figure out the resources that you need to get past, what wasn't possible before. That's really cool to hear. We have time for one more question. We have a question. How did you evaluate and choose which cloud services to use? Like evaluating using the stateless code engine versus virtual machines versus Docker and using Redis. It's just a lot of these different technologies. And how did you break down these high-level projects into these very concrete cloud services?
Yeah, I won't pretend that I had God's view of all the possibilities and I chose the optimal one. I kind of followed my nose, guided by pragmatism. The serverless, I've used serverless for a number of years. I like the ability to just simply specify the unit of a function that I want to run, define that somehow. It could be just a script, or it could be a Docker container that can run what I want it to run, and then just say, I don't know how you're going to do it, cloud service provider, but go do it. As someone who is not a cloud guru, I am drawn to serverless for that reason. And so that's what led me to Code Engine specifically. Redis was kind of, one of the drawbacks of serverless is the statelessness. And we needed some state in our active learning application because we needed to know how many, like I mentioned how there was this retraining criteria. We need to know when we meet that retraining criteria, and that's kind of a state. And so we needed a way to get that state in. And here I was, not knowing how to do that. And so I Googled how to do that. And compared a few different ways. You know, you can use cloud object storage, or you could use your relational database. But if you just need to record some simple bits of data, Redis is a really nice solution. So there may be others there. Cost was another factor for us. I've used VMs for similar types of applications, running all the time on instances that I provision myself, and it's just a lot more expensive when our workloads are bursty. Like we just run a job that takes a minute every 15 minutes, so why pay for the 14 extra minutes? So that also kind of led us to serverless.
That's a cool example of cost savings through cloud optimization. All right, well, I think that's unfortunately all the time we have for this session, but thank you so much, Hudson, for coming and sharing with us all of this information. We will take a 3-minute break and then resume at 10:30.
Thank you, Naomi.
Yeah.